Hi all, this is question number 35 from GATE 2019. The question says that we are given four statements, and the questions ask us to find which of these statements are true. So let's consider the first statement. The ring Z adjoint iota is a unique factorization domain. And if you know this fact that this ring Z iota is in fact an an, Eu- an Euclidean domain, okay, ED. Okay, and ED implies PID, and PID implies UFD. Okay, so this statement is actually true, that Zi is a UFD. And how to see that this is an ED? So let's consider A plus BI belongs to Zi, a random Gaussian integer, and let R plus Si belongs to Zi be a non-zero Gaussian integer. Yeah, so by the way, this Z polynomial ring, this ring is called the ring of Gaussian integers. Okay, so yeah, so we want, what do we want? We want to we want to write A plus Bi should be written as R plus Si times some quotient Q plus some remainder, right? And what do we want? Remainder is a Gaussian integer whose norm is less than R plus Si. That's what we want. And we can basically we divide this whole expression by R plus Si. So what this becomes, A plus Bi by R plus Si is equal to Q plus remainder by R plus Si. And what is remainder by R plus Si? The absolute value of this is less than 1 because of this thing. Okay, so we want to write this as this thing with this Q is a Gaussian integer plus something here whose absolute value is less than 1, strictly less than 1. That's what we want, and we ask, can we get it? So the answer is yes, we can. So we can so A plus Bi by R plus Si can be written as let's say that C plus Di, where CD belongs to Q, because like we can what do we call, rationalize this fraction, and we can get an expression in this form, C plus Di. Now so we have this lattice of Gaussian integers in Zi, right? So this is 0, this is 1, this is 2, and this is imaginary axis I, 2i, 3i. So C comma D are rational numbers, so this may not lie in lattice, but it will lie in some point inside some square, right? Unit square C comma D, and we can divide this square like this. Okay, so So basically, let's choose E, F, B integers such that uh, C minus E is less than equal to half and D minus F is less than equal to half. We can do that. We are basically choosing the nearest integer to D, nearest integer. So for example, if something C was 3/4, then E would be 1, and if C was 1/4, then E would be 0, right? So we are choosing the nearest integer close to C, and similarly for D. Now so let take Q is equal to what? E plus Fi. Then A plus Bi by C plus Di minus Q is equal to, this will be what? No, not C plus Di. This is R plus Si minus Q would be equal to C minus E plus D minus Fi. And the norm of this thing is norm of this, and this is less than equal to, by triangle inequality, 1/4 plus 1/4 square root, and this is equal to 1 by square root of 2. This is strictly less than 1. Yes, so basically we are done. We have proven that this is a Euclidean domain. We have produced a Q such that this term has absolute value less than 1. Okay. And as I said before, that once we prove Euclidean domain, then it will imply PID, and that will imply UFD. So it's the ring of Gaussian integers is a UFD. So this is true. The second statement is the ring. Second statement is the ring Z is a PID, and solution that 6 it can be written as 1 plus square root of minus 5 times 1 minus square root of minus 5. This can be written as 2 times 3. Okay. So and these you can check that these are like so these 6 have 2 different factorization in this ring Z adjoint square root of minus 5. So 6 so this ring Z square root of minus 5 is not UFD, therefore it cannot be a PID, because if it were PID, then it would not then it would be a UFD, but it is not UFD. Okay, so second statement is false. The third statement, we are given this polynomial. Yeah, so the third statement is that this x cube plus x plus 1 generates maximal ideal in z2x. Okay, so first thing to see that this is a cubic polynomial, and if cubic polynomial has a root, sorry, if so I claim that this polynomial is irreducible. Because this is a cubic polynomial, so if it were reducible, then it must have a root in z2, right? So, and this doesn't have a root in z2. So for example, 0. So let's take f of x is equal to x cube plus x plus 1. Then f of 0 is 1. F of 1 is also 1 in z2. Okay, so this polynomial is irreducible. It doesn't have a root in z2, and we know that in an irreducible polynomial generates maximal ideal in this ring. Okay, so this statement is true. What about fourth statement? This x to the power 6 plus 1 generates maximal ideal in z3x. So note that x to the power 6 plus 1 can be written as x square plus 1 whole cube. Okay, so x to the power 6 plus 1 doesn't generate a maximal ideal. Okay, because like x to the power 6 plus 1 would be properly contained in the ideal generated by x square plus 1. Okay, so it is not maximal, and this is like proper ideal of this ring R. Okay, so this statement is false. Alright, so the correct option is B option. First and third only are the correct options. Correct